So as we have seen, any homogeneous Poisson process with rate alpha has these properties. Namely, it has stationary increments. It has independent increments. That's number one. It has stationary and Poissonian increments. That's number two. And it starts from zero. That's number three. And we will prove this, at least we'll sketch the proof of this, is that 1, 2, and 3 are characterizing properties of a homogeneous Poisson process. Now, I have been telling you about inhomogeneous Poisson process. This is actually a good time to introduce what it is. Although we are not going to analyze it, it's good to know what it is, just to see the contrast. Okay? So in case of inhomogeneous Poisson process, the properties 1 and 3 will hold. So in particular, the process will start from 0, and it will also have independent increments property. But property 2, namely the stationarity of increments, will actually be replaced by a different property. The Poissonian increments will remain Poissonian, but the parameter will change. So 2 will be replaced by, for every s less than t, both st being non-negative real numbers, the difference nt minus ns will be a Poisson random variable whose parameter would be given by integral of a function r over the interval s to t. Now this function r would be a non-constant function defined on 0 infinity, taking values in positive reals. Okay, so this is a function whose domain is non-negative reals and range is positive reals. Codomain is positive reals. Now this function is going to be non-constant, so that the process becomes inhomogeneous, and this function will be called rate function or intensity function. Of course, we are talking about these as parameters, so all these integrals should be finite. So the function r should be such that all of these integrals are finite. Now this non-constantness of the function corresponds to the inhomogeneity of the Poisson process, as I've already mentioned. In the case of homogeneous Poisson process, however, the function r would be the constant function alpha, so that the integral of r from s to t just becomes alpha times t minus s, and therefore the difference nt minus ns will follow Poisson with parameter alpha times t minus s. Okay, and that has also is the distribution of n of t minus s, which gives the stationarity of increments in the homogeneous case. In the inhomogeneous case, however, the function r will be non-constant, and roughly speaking, a higher value of the function ru implies a higher probability of an arrival in a small neighborhood of u. This is just the intuition. Okay? So therefore, in the case of Salon example, r would be higher when we expect more customers to arrive, say between 10 to 11:30, okay, or 10 to 12. On the other hand, r would be lower in the early morning, say 7 to 8:30. So, okay, so that r will give you the probability, roughly speaking, of arrival. Okay, a higher r would imply higher probability of an arrival in a small interval around. Okay, so that's all I'm going to talk about inhomogeneous Poisson process. Now we'll go back to the homogeneous Poisson process. We'll actually sketch the proof of this result that says a process n dash t, a stochastic process, continuous parameter stochastic process indexed by non-negative real numbers n dash t, that satisfies, that enjoys independent increments property, as well as stationary and Poissonian increments property as described before, and it starts from 0. For if such a process n dash t exists, then it has to be a homogeneous Poisson process on positive real line with intensity alpha. Because this is the converse of the previous theorem, and I'm using the processes n dash, so that apparently we don't know their Poisson process, so that's why I'm using a different notation. just to separate it out from NT. Once we sketch the proof of this, we'll actually get the following result, which says, by the way, this theorem I'm calling theorem star star. I'm going to refer to this converse as theorem star star from now on. Once we prove this theorem star star, along with the previous theorem that we have proved, well, we have almost proved modulo 1 induction argument that I asked you to prove. We'll give this characterization result of homogeneous Poisson process, namely a stochastic process NT, a continuous parameter stochastic process NT, indexed by non-negative reals, is a homogeneous Poisson process on 0 infinity with rate alpha if and only if the process n dash t has independent increments like this. The process n dash t has stationary and Poissonian increments, which means this, and it starts from the point 0, namely n dash 0 equal to 0. Now, of course, this will be true, this characterization result will be true, provided we are able to prove theorem star star. Now, let's try to see how that can be proved. Suppose n dash t is indeed a stochastic process such that 1 dash, 2 dash, and 3 dash hold, which means 1 dash is this property of independent increments, 2 dash is the property of stationary and Poissonian increments, and 3 dash is the property of starting at 0. Okay. Now recall 3 dash just means n dash 0 equal to 0, and 2 dash just means n dash of t minus n dash of s is Poisson with parameter alpha into t minus s whenever s is less than t, whenever s minus t is negative. Okay, so that t minus s is positive. Now, if you combine these two, what you will get is that if you put s equal to 0 in this statement, you will get that n dash t follows Poisson with parameter alpha t, because n dash 0 would be 0, and this would be Poisson with parameter alpha t. So n dash t is Poisson with parameter alpha t, which will imply that n dash t will only take non-negative integer values. Also, whenever s and t are two non-negative reals such that s is strictly less than t, n dash t minus n dash s is a Poisson random variable by 2 dash, and Poisson is always non-negative. It always takes non-negative integer values, but in particular is non-negative. Therefore, n dash s is always going to be less than equal to n dash of t. So therefore, t going to np is a non-decreasing step function taking non-negative integer values. Of course, it's a random function because each nt is a random variable. So t going to np is a random non-decreasing step function taking non-negative integer values. Now, of course, this alone does not guarantee that NT is a Poisson process. The crucial question is how to show that n dash t, sorry, not NT, n dash t is a homogeneous Poisson process with the intensity alpha. By the way, there is a typo here, which I'm going to correct before uploading the slides, is that this should be n dash t. Okay? There's a typo here. So t going to n dash t is a random non-decreasing step function taking non-negative integer values.